Hi class, we are now in the last section of chapter 12. This is 12.6 buffers and biological pH. A buffer is a solution that resists changes in pH. So we're going to be looking at pH. So the cells that make up, a buffer. The cells that make up your skin, muscle, blood, and organs must remain in a very narrow pH range in order to function properly. The fluid inside cells typically maintains a pH of about 6.8, while the bloodstream maintains a pH very near 7.4. For instance, this isn't discussed in your book, but when there are burn victims that are burned really, really badly, most of them don't die from the burns. They die from their blood being out of the pH range because of all the effects of what's actually happened to them. So given the number of acidic and basic compounds present in the bloodstream and inside the cells, how do our bodies remain within these ranges? Our bodies use buffer systems to keep the pH at healthy levels. A buffer is a solution containing a mixture of acidic and basic components that resists change in pH. In the absence of a buffer, addition of a small amount of an acid or base can drastically impact the pH of a solution. So meaning it's going to jump really high on the pH or really low on the pH to be acidic. However, in a buffered solution, adding the same amount of acid or a base causes a much smaller pH change. So if it's a buffer, it's not going to jump as badly as it would be if there was no buffer solution. For example, let's begin with a sample of pure water. If we add a small amount of acid, so if we start here in the middle of pure water at a pH of 7, if we add a small amount of acid, the pH drops drastically. If we add a small amount of base, the pH increases drastically. So you can see this is almost 9, this is almost 5. The pH of two different may seem like it's not a big deal, but this is a huge difference here in between that. But if we repeat the experiment with a buffer solution, we see a different result. Adding the same amount of acid decreases the pH only slightly. Adding the same amount of base increases the pH only slightly. So you can see it goes down to 6.88 and increases to 7.12. How do buffer solutions work? Buffer solutions contain one of the following two combinations: a mixture of a weak acid and its conjugate base, or a mixture of a weak base and its conjugate acid. Both species must be present in large quantities. For example, animals contain a buffer consisting of H2PO4, which is this one here. There we go. Couldn't find the mouse. And that is dihydrogen phosphate ion, which is a weak acid. And this one here, this is dihydrogen, PO4 minus. And this one here is hydrogen phosphide ion. So let me repeat what this is. For example, animal cells contain a buffer consisting of dihydrogen phosphate ion, which is a weak acid, and hydrogen phosphate ion, which is its conjugate base. There we go. Chemically, we represent this buffer using this equilibrium. So you can see here we have the equilibrium going on with the equilibrium arrows here. The acid, which is dihydrogen phosphate, consumes excess hydroxide. The conjugate base, here we go, over here, consumes any excess protons. The ratio of H2PO4 minus to HPO42 minus will change, but the amount of proton and hydroxide present changes only slightly. So what it is that if there's hydroxide, it's going to react with any hydroxide, which is a base, and this one will react with anything that's acidic coming in, which will result in a proton, and it'll react with that and pushes it this way, where this one will push it that way. A buffer solution can be thought of as two guard dogs watching opposite directions. One component guards against an influx of acid, and the other guards against an influx of base. The bloodstream and the fluids between cells use different buffer systems. Based on carbonic acid and its conjugate base, the bicarbonate ion, when carbon dioxide dissolves in the bloodstream, it reacts with water to form carbonic acid. This acid partially ionizes to form bicarbonate ion. In this buffer system, the carbonic acid consumes excess base. while bicarbonate consumes excess acid. Certain conditions can cause the blood pH to fluctuate. For example, hyperventilation is a condition in which a person breathes abnormally fast, taking in more oxygen than the body needs. This condition is usually brought on by extreme stress or panic and causes dissolved CO2 levels in the bloodstream to drop. This in turn reduces the amount of H2CO3 present in the bloodstream, which is carbonic acid, causing the pH of the blood to quickly rise. While this situation may cause other symptoms, it can usually be brought into balance after normal breathing is restored. It is possible to overload a buffer. For example, if a large amount of acid is added to a phosphate buffer, eventually all the base will be consumed. At that point, the pH of the solution will change sharply. Buffers can also be adjusted to specific pH values. The pH of a buffer solution depends on the specific combination of acid and conjugate base and the concentrations of each component present in solution. So what are they saying about overloaded? It means that there's large amounts of, let's just pick one of them, because remember, it's got to be either a weak acid or conjugate base, or weak base and conjugate acid. So let's say that we pick one of these. It's in large combinations of both. You have the weak acid and a large volume of conjugate base, but eventually you can overload it by adding more and more and more of whatever it is that's going to cause it to react until there is no more of that. And once it's no more, the buffer's gone and it will jump in pH. That's what it means. It's not infinite. It's going to eventually run out, and then it's going to act like a normal solution such as water, and not a buffer, because it's not a buffer anymore. So again, here's a picture of what happens with pure water when acid and base are added, and then when a buffer solution. Buffers and biological pH. This explains this one will react with any hydroxide. This will react with any proton, and this will push it this way. This one will push it this way, depending on if it's reacting with an acid or a base. Which compound would be best combined with aqueous HClO to produce a buffer solution? So the one thing you got to remember here, that it's got to have the same foundational species in it. So if it doesn't have the same foundational species, you're not dealing with the same compound. So it's going to be D, because the only thing that's missing there, the difference, is the cation. A buffer is made by mixing aqueous sodium nitrite and aqueous, I forgot what this one is, it's nitrous acid. A few drops of concentrated HCl are added to the buffer. Which species reacts with the HCl? That's going to be the NO2, of course. Remember, sodium's just in a sense a spectator ion. We're not interested in that. It's going to react with this.